Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at molecular geometry. So the thing about molecular geometry, at least at this stage, is we're using the VSEPR model, and that is a rather intuitive model if you get into geometry. However, at the outset, it's much easier to just simply memorize how many atoms and electrons are on the central atom in order to determine what the geometry is supposed to be. Which is to say, simply associate a generic molecule with a central atom, figure out how many atoms are attached to that central atom, and how many lone pairs are attached to that central atom, and that will indicate what the geometry of the molecule is. And you'll have to take time to commit to memory the types of geometry and the generic formulas that equal that geometry. So for each of these, we're going to start by drawing out the Lewis structure or molecular structure of the molecule. So for the first one, we have ammonia. So we're going to do N, and it's going to be attached to a hydrogen. Edit. We'll start with ammonia, which has a central nitrogen, and it has a hydrogen coming off in 3 different areas. Now, if you recall, as of right now, we currently are using 6 electrons total. Each hydrogen contributes 1, but ammonia has 5 total. So if ammonia has 5 and there are 3 hydrogens, each contributing 1 electron, we have a total of 8 electrons. And there are only 6 that are committed to bonds. You can't make double bonds with hydrogen, so we're simply going to do a lone pair on the nitrogen. In the generic form, this would be called AB3E. Okay? And when you look at your chart, whenever you see AB3E, you're going to have it as trigonal planar. Which kind of looks a little bit like this. We're going to draw it a little more accurately. And you'll have the hydrogen coming over here, and the hydrogen coming over here, and one down there. And you'll see what basically is happening is the lone pair actually, despite the fact that it's a lone pair, takes up more space than the bond does. So it's pushing the atoms that are connected to the central atom away, because the lone pair does take up more space. Let's take a look at our next molecule. So bromine tetrafluoride, each one of these is a halogen. So each one is going to contribute 7 to the total, which gives us a grand total of 42 electrons. Now, halogens like to make single bonds. So let's start by putting bromine as our central atom. And obviously, we're going to have that expanded octet. As you can see, we've got fluorine here, fluorine here, fluorine here, and one more. So that's 5. And each of the fluorines is going to have 6 electrons surrounding it. Okay. 6 electrons around each fluorine. 6 times 5 is 30, plus 2 for each bond. So now we're up to 40. So 42 minus 40 leaves us a remainder of 2 electrons. So we need to attribute those 2 electrons, and because the octet is filled for fluorine, and fluorine is not in the grouping, it's in period 2, it cannot have the expanded octet. However, bromine, being in period 4, can have the expanded octet. So we'll just simply put 2 more electrons here. So the generic formula for this molecule is going to be AB5E. The A signifies the central atom. It's always just going to have one A. The B is the number of atoms attached to the central atom directly. There are 5 of them, 5 fluorines. The E signifies the number of lone pairs on the central atom. And again, in this case, there's only 1. So that's why we have AB5E. And when you look that up on the chart, after you've memorized it, of course, you can find that that is square pyramidal. Okay, and actually, in looking at this, that's kind of what we did already. Square pyramidal, the only difference would be that the fluorines might be a little more bunched together up at the top. Otherwise, it's relatively accurate to the geometry. Now let's look at sulfur tetrafluoride. Sulfur tetrafluoride has 4 fluorines, and sulfur is in our expanded octet. So we know that we can make more bonds with sulfur than just 4. But let's see if we're actually going to need it. So there are 7 for fluorine, and there are 4 of those. So we're looking at 28 plus sulfur adds 6 to that. So now we're up to 34 electrons. So let's see if we can use them all up. We've got sulfur as our central, and we've got fluorines sticking off of the sulfur. And each fluorine will have 6 electrons. Again, halogens like to make a single bond. They don't want to make a double bond. So we're just going to keep it as a single bond. So with each of the fluorines having 6 lone electrons on them, 6 times 4 is 24, and we've got 8 electrons used in bonding, so that gives us 32. So we're 2 electrons away from our total of 34. So we're just going to put a lone pair on the central atom, sulfur. So that gives us an AB4E. Again, the 4 and AB and the B, edit. Again, the 4 in B4 is indicative of the number of atoms surrounding the central atom. We've got 4 fluorines surrounding the sulfur, so our B is 4. We only have 1 lone pair, so E is just left at E. And this, on your chart, you'll note, it's called a seesaw. And what it looks like is like this. You've got your lone pair, you've got your sulfur, and all those fluorines are going to stick out like that. They're all really kind of trying to get away from that lone pair. Okay? So that's our seesaw. Our next one is phosphorus tetrachloride. Again, phosphorus is a period 3 atom and thus can have an expanded octet. So let's take a look. Phosphorus is going to have is going to contribute to the electrons 5 electrons, and chlorine contributes 7. So 7 times 5 is 35, plus 5 is 40. So let's see if we can use those up. Phosphorus, and we've got 5 chlorines attached to each of them, attached to the central atom. And each of the chlorines has 6 electrons hanging out. All right, so let's take a look at this. We have 6 electrons on each chlorine. There are 5 chlorines. That's a total of 30 electrons that are free. And then the bonded electrons, 2 per bond, so that's a total of 10. 30 plus 10 is 40, and we already said that we needed 40 electrons, so there is no lone pair on this. That makes this an AB5. And if you look at your chart, AB5 is trigonal bipyramidal. Okay, and that's essentially just going to be, you have your phosphorus here. It's going to be in the plane, more or less, with the chlorines. Except for one chlorine, which is going to stick out. Okay, so that's trigonal bipyramidal. And that's exactly what that looks like. Well, not exactly. Okay, last one is one of the most essential molecules, water. And it's actually quite easy and complex all at once. So we have our central atom of water, and we know we're going to have a hydrogen and a hydrogen. Water has 2 electrons from the hydrogens and 6 from the oxygen, so that's a total of 8, and we've only used up 4. So you're going to have 2 more lone pairs on the oxygen. In the generic form, this would be called AB2E2. That means that you have 2 atoms on the central atom, attached to the central atom, and 2 sets of lone pairs on the central atom, which, when you look it up in your chart, you'll find is bent in shape, which makes it look like, kind of like this. And that's the basis for molecular geometry. I encourage you to take time to practice some of these and definitely work to commit to memory the generic form of the various formulas and their corresponding geometries. You don't have to memorize that water has a bent molecular geometry, but you should know that AB2E2 is bent, so that it's very easy for you to determine, based on your structures, that water is in fact a bent molecule.